Hi everyone, welcome back to AWS Julie. We're continuing our new playlist, which covers machine learning fundamentals to help you prepare for your AWS Certified Machine Learning Engineer Associate exam. And we're going to pick up where we left off from the last lesson and cover Domain 2, Task 2.3, which is to analyze your model performance. So let's talk about different calculations that can be used to evaluate the performance of a model. A confusion matrix represents the confusion of the output of a model that you are testing. It represents the results of the testing of the model and how confused the model is. An example is image classification. So let's say that we're classifying images as a yes or no. Yes, images are fish, and no, images are manatees. Once the model releases an output, that output is added to the confusion matrix. Along the top of the matrix is the reality of the output, or the predicted class from the model, and along the side is the model output or actual class. And a confusion matrix gives you a high-level comparison of how predicted classes match up against actual classes. So for our first image, we go to the left of the model output and down from the reality. And this cell represents a true positive because it is correct that this is an image of a fish, and the output from our binary classifier is a fish. So it is correct. And we repeat this process. So this time, it makes a prediction that it is a fish, but the image is actually a manatee. And this time, we will go from the model output section of the fish, but from the reality section, it is actually an image of a manatee. So this value is a false positive. The model predicted a positive, but it was not a fish, so it is a false positive. And if we do this again, the machine learning model predicts it can see an image of a manatee, but the image is a fish. So this is wrong, and this is represented in the confusion matrix as the model output in the manatee section and the reality section down to the fish. And this represents, again, a false negative. And this process is continued for the confusion matrix. With a model that is performing well, we want to see high values for the true positive and true negative. And I'm not talking about the true positive rate or true negative rate. We will talk about rates in a few minutes. A confusion matrix maps out the statistics of how well a model has performed, and for this lesson we used a binary classification. But you can also use a confusion matrix for multi-class classifications by calculating the values against all other options, and then these values we have calculated through the confusion matrix can help us calculate other values to understand the performance of the algorithm. So let's move on and talk about another way to measure the performance of our model and talk about accuracy. And throughout this course, we've mentioned the accuracy of the model, but in this lesson, we are specifically talking about the mathematical equation. The machine learning definition for accuracy is the number of correct predictions the machine learning model has made divided by the number of predictions. Accuracy is a simple way to measure the performance of a model, but it's not great at actually measuring the overall performance. So let's talk about a data set with the labels and predictions that a model has made. So first we count how many predictions there are, and there are 9 predictions. Now we count how many of the predictions are correct and where the model was right. So that would be where the label matches the predictions. So we want to count both the true positive and the true negatives, and there are 6. So then we divide 6 by 9, and that equals 0.667 or 66.7% accurate. Let's pause here and jump back to what I said earlier, that accuracy is not great at actually measuring the overall performance. So from this example so far, do you understand why that is? And apologies if you can hear the lawnmower in the background. Well, the issue can sometimes be with the true negative, because in this case, we are adding both the true positives and true negatives together. So if one of these is high and the other is low or 0, then it could mean our accuracy score is also high. So for example, let's talk about this data set. And the accuracy of this data set is 8 out of 9. So we get an accuracy of 0.889 or 88.9% for this model. But all the predictions are no. So this model could be broken and might not be working with our data, but we have an accuracy of 88.9%. So we need to know what other measures we can use to work with unbalanced data sets, and that there are other measures to use depending on the kind of problem you're trying to solve. So let's continue on with task 2.3, which is to analyze our model performance, and we're going to talk about precision and recall. You will use precision and recall in everyday machine learning life when you're trying to understand the performance of a model. But let's make sure we understand the difference between precision, accuracy, and recall. Let's pause for fundamentals and ask a question. What are other machine learning terms that mean the same thing as precision and recall? Well, we have positive predictive value, which has the same meaning as precision, and sensitivity or true positive rate, which has the same meaning as recall. And going forward, I will use precision and recall because that's what is preferred with AWS, but there are multiple terms that have the same definition. Precision measures the actual positives from the predictive positives, and the formula for precision or positive predictive value is the true positive divided by the true positive plus the false positive. The answer will be 0 or 1, and 1 or the higher value is better or more precise. And if we use this confusion matrix and apply the precision formula, we will have 10 divided by 10 plus 3, which equals 0.769 or 76.9%. And this is okay, but to have a better performing model for precision, we would want to reduce the false positive number of 3. So let's change our numbers and swap the true positives and the false positive numbers to see how it affects the precision model. So now we have 0.231 or 23%, and this shows the model performing not as well. Precision helps you focus on the true positives by detecting true positives, but you can also use recall. So before we move on to recall, I want to mention that if you change the false negatives or true negatives, it does not affect the precision values. Remember, recall is also known as sensitivity or true positive rate, and recall measures the actual positives that are predicted as positives. Again, that value is 0 to 1, and the higher value is better. And the recall formula is true positives divided by true positives plus false negatives. And I want to make sure that we understand the differences between these two formulas. Precision is true positives divided by true positives plus false positives, and recall uses the formula of true positives divided by true positives plus false negatives. And the focus of the formula is looking at the positive rates of false negatives. So let's add our numbers into our confusion matrix, and we get 0.909 or 91% recall or sensitivity for this model. And just like with precision, let's change the values with a lower true positive value and a higher false positive value. And the recall changes to 0.091 or 9%. So let's pause here again because I want to point out that if you change the false positives or true negatives, it does not affect the recall value. So it is important to realize that recall and precision does not give you a whole picture, but it gives you a focused picture on the true positive number. And here's how I remember the difference between precision and recall. Remember, I grew up in a scuba diving shop, and a lot of my analogies relate back to my childhood and my teenage years, and I remember precision and recall using a scuba diving analogy. So in scuba diving, you always have a buddy, and my buddy was usually my brother Lee, who loved to spearfish. And I think of precision as a dive with my brother where he is looking for a specific type of fish, which was usually a grouper. So with precision, my brother is looking to capture all the groupers he spots. So groupers are the positive value, and they are the green with sort of the pink outline fish that you see that he has already caught in the boat. Now let's compare this to recall. For a high recall dive, Lee doesn't care about false positives. So instead of spearfishing and catching just the groupers, he uses a bucket to catch as many fish as he can. And in this case, he has most of the positive values because he's captured most of the fish in the area that we were diving in. He also has negative values too, but what is important is that he has all of the positive values. So for high precision, we make sure all the fish caught are positive values. With a high recall, we make sure we have all of the positive values. And remember, groupers are the green fish with sort of the pinky nude outline, and there are positive values in this example. But in the real world, there are examples of scenarios you would use for precision and recall. And let's jump back to my scuba diving. And when I was teaching elementary students to snorkel, I needed to make sure that the content I used to teach them was safe for their age ranges. And this is the same for content on the internet. So a real-world example of when you would use high precision is classifying content on the internet as safe for children. A personal example of recall is when I'm creating AWS exam prep content to help students pass their AWS certifications with my courses on AWS Skill Builder. And one of the things I always do is I always try to include all the content that you may or may not see on your exam. So I cast my net so wide to ensure that you have the content that is relevant to the different AWS certification exams. In a real-world machine learning scenario and use case for high recall might be using a machine learning model to classify financial transactions to detect fraud. So let's talk about specificity and the false positive rate, which are different ways to look at the same thing. These are not used as frequently as precision and recall, but I did want to include them because I like to include everything that you possibly might need. But let's start with specificity, which is equal to the true negatives divided by the true negatives plus the false negatives. Specificity has a direct relationship with the false positive rate because false positive rate is 1 minus specificity. False positives measure the actual negatives that are predicted as positives. Again, the value is 0 to 1, but with false positive rate, the lower value is better. Let's continue with task 2.3 to analyze the performance of our models and talk about different techniques that we use and metrics to measure the performance of our models. And we can use these performance models that we've discussed so far in the last few lessons, such as precision, recall, accuracy, false positive rate, and specificity to determine which model best suits the requirements depending on the correct parameters and thresholds that are inside our models. Let's start with receiver operating characteristics or ROC. The ROC curve is a graphical plot that shows the diagnostic ability of a binary classifier system as its discrimination threshold is varied. So to compare different classifiers, it can be useful to summarize the performance of each classifier into a single measure. One common approach is to calculate the area under the ROC curve, which is AUC. AUC measures the ability of the model to predict a higher score for positive examples as compared to the negative examples. Since AUC is independent of the selected threshold, you can get a sense of the prediction performance of your model from the AUC metric without picking a threshold. So let's jump back into the high recall spearfishing scenario that we were just talking about, and we're trying to get all of the fish. And let's dive a bit deeper and talk about how we can set the threshold to achieve the needed recall without recalling all of the fish. And this is where ROC can help. On this graph, the y-axis, we have values and the true positive rate, which remember is also known as recall and sensitivity. Then on the x-axis, we have the false positive rate, which is also known as the specificity with some values. And the ROC is the line we plot on this graph. And you may be asking, Julie, how do I do that? Well, if you have a binary classification model that you've trained, you input the data and then you get an output of the true positive rate and a false positive rate. So how do you plot these single values on our graph? You plot these values on the graph by altering a threshold or a characteristic about the way the model works. And ROC helps us figure out a way and how you would change that threshold. And then the area under the curve of the line is the area under the curve, or AUC. So the ROC is used to help choose the optimal model or optimal threshold value for your requirements. And the AUC is the representation of the overall algorithm or model that you're using. And the unicorn value is always 1. And that is a model that classifies everything correctly, which usually doesn't happen. So let's bring back a graph we were using earlier under our logistic regression lesson. And you will see that the black line is our model that we've created between the positive values at the top and the negative values at the bottom. And with the overlap, there's not a perfect place to place the threshold between the 2 points, or 2 sets of points. And remember, if we use high recall, we will get all the positives, but also all the negatives too. So we have to adjust the recall value using ROC. So if we set the threshold line at the very beginning of the line, then everything to the right is positive and anything to the left is negative. And there is nothing to the left. But in reality, the upper data points are the positive values and the negative values are on the bottom line are also classified as positive with the threshold line set at the beginning. So we add in 2 6s and 2 0s. And then we can calculate the TPR, which equals 1. Then we can calculate the FPR, which also equals 1. And we end up with a point on our graph at the upper right-hand side. So let's move the threshold to the right, and the difference here is in our negative values. Here, 2 of the negative values have been correctly classified. And here is the calculations that we did for that. And at this point, we have taken a step back and we have reduced the false positive rate. So let's move our threshold again to the right. And at this point, we have started to lose our true positive values. And our true positive value is now 4. And 2 positive values are now being misclassified. And the negative values now have 5 values correctly classified. And here is the calculations and where we have moved since then. And you'll see that we have moved further to the left. So let's move our threshold line again. And now all of the negative values are classified correctly, but 4 positive values are classified incorrect. And now the false positive rate has dropped down to the y-axis. So let's move our threshold line one more time all the way to the right-hand side. And now all our values are classified as a negative value. And we end up with this data point on the bottom left-hand side of our graph at 0. And these are the points for the ROC, and you can connect the dots together as best as possible. And then you see this area under the curve too. Now, how do we use this to determine the threshold to use for the business requirements? So for high recall, you need to make sure you have identified all the true positives and all of the true negatives correctly. And at this point, you look at the knee in the graph where there is a significant change of angle that indicates the highest sensitivity with the best false positive rate. Could you also choose another point? Yeah, you can also choose other points, but you want to find the best value, and that is going to be where you have the best specificity and with the best sensitivity, if that is the metric that you're trying to use to meet your requirements. Let's continue on with task 2.3 to analyze our model performance and talk about using metrics to analyze the performance of machine learning models and talk about F1 score. The F1 score is an accuracy measurement that you can get by looking at the precision and recall together. Let's look at the confusion matrix from this model. You need to calculate the precision of this model. Do you remember the precision formula? The formula for precision or positive predictive value is true positive divided by true positives plus the false positive. What is the formula for recall? The formula is true positives divided by true positives plus false negatives. So here we get a value of 0.04 for the precision and a value of 0.86 for the recall. The F1 score will give you one value to represent how well the model performs. The F1 score is a type of average. It is a harmonized average of precision and recall, and the formula is 2 times the precision multiplied recall divided by precision plus recall. And the F1 score for this is 0.08 or 8%. And this tells us that the model is not great. But after you've built your model, you can evaluate how well your model performed on your data before using it to make predictions. You can use information such as the model's accuracy when predicting labels and advanced metrics to determine whether your model can make sufficiently accurate predictions for your data. But let's pause and talk about how to create a model quality baseline in AWS to compare your model predictions in AWS. You can use Amazon SageMaker Ground Truth with ground truth labels in a baseline data set that you store in Amazon S3. Then you can use a training data set as the baseline data set. The baseline job calculates metrics for the model and suggests constraints to use to monitor the model quality drift. But to create a baseline job, you need to have a data set that contains predictions from your model along with labels that represent the ground truth for your data. Model quality monitoring jobs monitor the performance of a model by comparing the predictions that the model makes with the actual ground truth labels that the model attempts to predict. To do this, model quality monitoring merges data that is captured from real-time or batch inference with actual labels that you can store in an Amazon S3 bucket, and then compare those predictions with the actual labels. To measure your model quality, Amazon SageMaker Model Monitor uses metrics that depend on the machine learning problem type. So for example, if your model is for a regression problem, one of the metrics evaluated is the mean square error, or MSE. So for your exam, make sure you check out all the different machine learning problem types and metrics used in Amazon SageMaker. For the exam, also ensure you understand model fit because it is important for understanding the root cause for poor model accuracy. You can determine whether a predictive model is underfitting or overfitting the training data by looking at the prediction error on the training data and the evaluation data. And we've talked about model fit several times so far in these lessons. Your model is underfitting the training data when the model performs poorly on the training data. This is because the model is unable to capture the relationship between the input examples, often called X, and the target values, often called Y. Your model is overfitting your training data when you see that the model performs well on the training data, but does not perform well on the evaluation data. This is because the model is memorizing the data it has seen, and it's unable to generalize with the unseen examples. Poor performance on the training data could be because the model is too simple, and performance can be improved by increasing the model flexibility. To increase model flexibility, you could add new domain-specific features or more feature Cartesian products and change the types of feature processing used, such as increasing your n-gram size or decrease the amount of regularization used. If your model is overfitting the training data, reduce the model flexibility and consider using fewer feature combinations. You can decrease the n-gram size and decrease the number of numeric attribute bins or increase the amount of regularization used. Accuracy on training and test data could be poor because the learning algorithm did not have enough data to learn from. So to improve performance, consider increasing the amount of training data examples and increasing the number of passes on the existing training data. We know that machine learning is an iterative process, and when we're solving a new use case, we iterate through various parameters to find the best model hyperparameters that can be used to solve the identified challenge. Over time, after experimenting with multiple models and hyperparameters, it becomes difficult for machine learning teams to manage model runs to find the optimal one without a tool to keep track of the different experiments. And this is where you can use AWS to help. And that's where you can use AWS to really help you understand and track all of that for you. So that's the end of Domain 2. In our next lesson, we will cover the fundamentals for Domain 3, which is deployment and orchestration of machine learning workflows.